champions. Right now we have an algebraic structure called as a vector space, and every element of vector space is called as a vector. So let us consider 4 vectors from the vector space V. No doubt you may take any number of finite elements of vector space, but right now I am considering only 4 vectors from the vector space V. So V1, V2, V3 and V4, these are the vectors from the vector space V. The first 2 vectors are having relation with each other. That means the first vector is 3 times the V2 and the third and fourth vectors are not having any relation with each other. So therefore, using the simple algebra, we can write this equation as a V1 minus 3V2 is equal to 0. Now I will write this is 1 into V1 plus minus 3 into V2 plus 0 into V3 plus 0 into V4 is equal to 0. And if you observe the left hand side, this is a linear combination of 4 vectors V1, V2, V3 and V4. And the value of this linear combination is equal to 0 on the cost of the scalars. If I am supposing this first scalar as alpha 1, alpha 2 is equal to minus 3, alpha 3 is equal to 0, alpha 4 is equal to 0, then this linear combination is equal to 0 on the cost of the values of the scalars which are not all equal to 0, and still I am getting linear combination of 4 vectors is 0. Now let us see another expression. I am considering again 4 vectors W1, W2, W3, W4 belongs to vector space V. Now I am considering it's a linear combination with 4 scalars beta 1 W1 plus beta 2 W2 plus beta 3 W3 W3 plus beta 4 W4 is equal to 0. And note that in this linear combination, the value of linear combination is 0, but on the cost of these 4 scalars, beta 1, beta 2, beta 3 and beta 4, all are equal to 0. If you observe both the expressions, in both the expression linear combination is equal to 0, but here not all scalars are 0. Here all scalars are 0. Therefore, this concept is linear independent, and this concept where all are not equal to 0, this concept belonging to linearly dependent vectors. So here V1, V2, V3, V4 are linearly dependent vectors over the field F, and here W1, W2, W3, W4 are linearly independent vectors over the field F. Now you have to write the definition of linearly dependent vectors over the field F, and you have to write linearly independent vectors over the field F right now. Now after this clip you will get one clip on which the definition of linearly dependent and independence are there. You have to write by pausing the video. Okay, now we will see the next result, and in that result n vectors are given from the vector space V and they are linearly independent. It is given to you, and we have to show that every element in their linear span has a unique representation, and we have to prove that representation of every element of the span is unique. Alright, so in this theorem, the next slide you will see the detailed proof of the result, but now I will give you how to prove this. In this result, n vectors are given to you and these are linearly independent. So let us consider v1, v2, vn. These are the members of V which are linearly independent. This is given to you. And now we will take one element x from the linear span. We know that every element in the linear span expressed as a linear combination of the given vectors. So for the linear combination we need scalars. How many vectors are given? N. Therefore how many scalars we need? N. And we consider some scalars alpha 1, alpha 2 up to alpha n from the field F. These are called as scalars, and we write this x as a linear combination of these vectors. So alpha 1 v1 plus alpha 2 v2 up to alpha n vn. So this is a linear combination and it is an element from the linear span of v1, v2, vn. Now we have to show that this expression is a unique expression. So for that purpose, let us consider the same x but with other scalars. Now we will find some other scalars, beta 1, beta 2 and up to beta n. So this x can be written as beta 1 v1 plus beta 2 v2 up to beta n vn. Now both are equal, therefore we can equate the left side of these expressions, and if you transfer all the terms to this side, you will get alpha 1 minus beta 1 v1 plus alpha 2 minus beta 2 v2 plus up to alpha n minus beta n vn is equal to 0. And keep in mind, these vectors are linearly independent. This is a linear combination equal to 0. This implies that all the scalars involving in this linear combination are all equal to 0. Therefore, we get alpha 1 minus beta 1 equal to 0, alpha 2 minus beta 2 equal to 0, and alpha n minus beta n is equal to 0. So we have proved that alpha 1 is nothing but beta 1, alpha 2 is equal to beta 2, and up to alpha n is equal to beta n. That means if you express the same x with same v1, v2, vn with other scalars, then at the end two different scalars are coincide, and therefore we can say that the expression is unique. Now you will write the detailed proof from the next slide. Okay, now we will prove the next result, and in this result they have given n vectors from the vector space V, and just we have to prove that these vectors are either linearly independent or that is very important, or any one vector among these n vectors. Let us suppose that vector is Vk. That vector Vk can be expressed as a linear combination of its preceding vectors. That means we have to show that the given vectors are either linearly independent, or one vector among these n vectors can be written as a linear combination of preceding vectors of that selected vector. Now how to show that? So in this case they have given us n vectors. So suppose v1, v2, vn are vectors from the vector space V, and now we have to show that what is the possibility of these vectors. As far as whatever I know, that when the vectors are given to you or given to us, then either they are linearly independent or linearly dependent. So we can write these vectors can be linearly dependent or can be linearly independent. But when these vectors are linearly independent, then there is nothing to prove, because already we have proved that these are linearly independent. But the problem is, if we suppose that these vectors are linearly dependent, then we have to show that the one vector, so we are selecting this one vector, suppose these are the vectors. I am writing these vectors like this. You just see this is k minus 1, vk plus 1 up to vn is, these are the members of V. Now these are, I am supposing, linearly dependent in the second case. Then we know that using the definition of linearly dependence, there exists scalars alpha 1, alpha 2 up to alpha n, which all not are equal to 0, such that alpha 1 v1 plus alpha 2 v2 plus up to alpha n vn is equal to 0, and these alpha 1, alpha 2, alpha n not all equal to 0. So since all scalars are not equal to 0, we can find a greatest integer k in between 1 and n, such that alpha k is non-zero scalars and all other scalars greater than this are equal to 0. So there exists this type of a scalar for the greatest k. Right, now I am putting these values of scalars in this expression, so automatically the expression apart from this k plus 1, k plus 2 will become 0, because all these scalars are 0, and hence I am getting alpha 1 v1 plus alpha 2 v2 up to alpha k vk is equal to 0. Alright, now transfer all the terms rather than this alpha k vk to that side. So I'm getting alpha k vk is equal to minus alpha 1 v1 minus alpha 2 v2 up to minus alpha k minus 1 vk minus 1. Look at this element. This is a scalar from the field f. F is a field. This is not equal to 0. Already we have considered, and we know that in the field every non-zero element possesses its multiplicative inverse. That means inverse of alpha k exists in f, so we can take its benefit. Just take the alpha k inverse, multiply to both sides, we will get alpha k inverse into alpha k, that is the multiplicative identity. 1 into vk is vk is equal to minus alpha 1 alpha k inverse v1 plus minus alpha 2 alpha k inverse v2, and so on. We'll get the last element is minus alpha k minus 1 alpha k inverse, that is vk minus 1. These are the scalars. This is a multiplication, and field is closed under multiplication. So multiplication of these two scalars we can denote it by another scalar, that is lambda 1. So it is vk is equal to lambda 1 v1 plus lambda 2 v2 up to lambda k minus 1 vk minus 1. And look at this. This is vk. I have written in the form of linear combination of its preceding vector. That means linear combination of v1, v2 up to vk minus 1. And that's why we have proved that when the n vectors are given to us from the vector space V, then either they are linearly independent, or one of the vector vk among the v1, v2, vn can be expressed as a linear combination of its preceding terms. Now, detailed proof of this result you may write after this session. Well, now we would like to define basis of vector space V. So, to define the definition, we need one subset S of vector space V containing some elements. And if this set will satisfy two conditions, then this subset of V is called as a basis of vector space V. So for that purpose, I am defining basis. So consider one subset of vector space V, and if the elements of S will satisfy two conditions, then this subset of V is said to be basis of vector space V. And I'm very interested to know what are these two conditions. First is all the elements of S are linearly independent over the field F, and another second condition is linear span of S is equal to V. So linear span of S is equal to V. This is the second condition, and all elements in S are linearly independent over the field F. So the basis, in short, basis of vector space V is nothing but the subset of vector space V containing the largest in number of independent vectors which will generate all the elements of V. The LFS of V, its meaning is that the linear combination of all the elements of S it will generate the elements of V, and that's why this S is called as a basis of vector space V. Now detailed definition you write now. Alright, now we will see the next result and the last result of this video. We have defined already what is the basis of vector space V, and now basis containing some elements, and suppose that basis of vector space V containing n elements v1, v2, vn. No doubt, according to definition of basis, these elements are linearly independent. But another set of vectors w1, w2 up to wm claiming that they are linearly independent, then the question arises whether these vectors which are only linearly independent, whatever the number they have, m numbers, m vectors, linearly independent vectors, what is the relation between number of elements in the basis and number of elements of independent vectors? And the result is the number of independent vectors are always either equal to number of elements in the basis or less than number of elements in the basis. That means no vectors claiming they are linearly independent whose number is greater than number of elements in the basis. So that we have to prove now. So basis is given and n elements are given. So v1, v2, v3 up to vn are basis elements. All right. And w1, w2, wm are linearly independent vectors, and we have to show that this number of linearly independent vectors is greater than less than or equal to n. This is, we have to show that. Okay, now consider these n vectors. These are the basis element, therefore they are linearly independent. And this is a basis, that means every element of the vector space we can write in terms of linear combination of basis elements. So I can take one element from the vector space V. So what should be that element? So I'm considering Wm. No doubt this is also a member of V, therefore we can take Wm as a vector from V. So Wm can be written as linear combination of basis elements, because these are the basis elements. Now Wm is depend on these vectors, therefore when I shall write this set of this vector Wm, v1 up to vn, so this set containing n plus 1 elements, and therefore this is depend on this, and hence this set of vectors are linearly dependent. And we know that every proper subset of linearly dependent set span vector space V, and therefore this set span vector space V, and therefore it's a proper subset will become basis of vector space V. So how will construct a proper subset of this set? So what I'm doing now, this is a base. I'm considering the next base that would be the proper subset of this set. So I'm taking one element as Wm, and remaining n elements I will escape at least one element. So whatever the remaining elements I will denote by I1, Vi2 and Vik. Note that this k is less than or equal to n minus 1. That means you may escape one element or two element or three element or four element and more elements, but at least you have to escape one element from these n vectors v1, v2, vn. Now Now this is a base, that means any element from the vector space V can be written as a linear combination of these elements, right? So I am considering the one element from the V, that is Wm minus 1. Now it can be written as beta 1 Wm plus beta 2 Vi2 plus up to beta k Vik. Now this is depend on all these vectors, therefore again this set similar to this n minus 1 Wm Vi1 Vi2 and Vik, this set become a set of linearly dependent vectors, and therefore it spans vector space V, and therefore the proper subset of again this set will become a basis. So continuing in this way, we will construct B2, B3, B4 like that. What is the concept behind this? If you see here, we have added two vectors from the W's. On the cost of, we have to escape at least two elements from the all V's, at least two. When we added three elements from the W's, we have to escape at least three elements from the V1, V2, Vn. So continuing in this way, finally we will get, so continuing in this way, we will construct the next basis of the vector space V. Now finally, if we will construct a basis B in which we have added n minus 1 elements from the W's, so starting with W2, W3 up to Wm and some V, V1, V2, that's all. Now this is also linearly dependent set, and therefore its a proper subset will become a basis, and every element of the V can be written as a linear combination of these vectors. But the problem is how many elements we have to escape from the V1, V2, Vn. That is the very much problem. Suppose that I'm not taking any one element from the V1, V2, Vn. So only these elements are left in this set, and therefore the element of the V, that will be the W1, if we take another element from V, that can be written as a linear combination of these vectors. 3 lambda m Wn, because we have not taken a single V from the V1, V2, Vn. So this should be happen. And if you see, W1 is depend on W2, W3, Wm, therefore W1, W2, W3 up to Wm will become linearly dependent. But in the result, W1 to Wm all are linearly independent. Therefore, we can't write like that. Therefore, whatever I have assumed that this no element should be come from V1, V2, Vn, that assumption was wrong, and that's why we have to take at least one element from the V. At least one. So once we say that at least one element from the V, that means that we have to escape n minus 1 elements from the V. And if we observe that from the back B1, B2, the number of elements, this is observation from this procedure, elements added from W's less than or equal to number of elements escapes from V's. So at least one should be here. That means we may escape n minus 1 elements. So the number of elements added from the W's are m minus 1 less than or equal to the number of elements escapes from the V's. These are n minus 1. So minus 1 get cancelled, and you will get this result, and we have proved that number of linearly independent vectors are always less than or equal to number of elements in the basis set of vector space V. So detail, this is the very big theorem, and we have reasoning to prove this. So later on you will see the detailed proof of this theorem in next few minutes. You will write and enjoy the mathematics. Bye bye.